All right. So please join me in the new classroom for the Slido stuff. Dun dun dun. Okay, I think this is kind of what I'm going to fall into for my new formatting. Is I'm going to have a Q&A where you can ask questions while I'm lecturing without interrupting my flow. And it'll be right before when I do a question. Okay? And then my question is then going to have like a quiz sort of format. And then we'll go on to answering that question. Okay. Is that making sense so far? Okay, I know I'm upping my game. Keep in mind that like I got access to everything after I started teaching. So this is configurational isomers. I know we're going on the flow chart now again, right? So don't forget that we've been working through this flow chart this entire time. So we start on isomers, right? And then we've talked about constitutional isomers so far, right? Okay. So do they have the same connectivity? No. Constitutional isomer or structural isomer, right? Do they have the same connectivity? Yes. Okay. And now we're going to go on to that. They could be stereoisomers. Okay. Or what type of stereoisomer can they be? So again, configurational isomers are going to have the same connectivity. If they have the same connectivity, they're going to be stereoisomers. Okay. So remember, this is how they're configured in three-dimensional space. That can be different versus how they're connected together. Okay. These are the same names for the same thing here. So configurational isomers or stereoisomers. Okay. Is everybody okay with that in terms of terminology? Kind of like a stereo system can be configured in three-dimensional space to give you different sounds, right? Okay, so there's going to be two types to these stereoisomers. There's then the enantiomers, and these are configurational isomers. They'll be mirror images of each other. There's the diisomers. They're going to be configurational isomers that are not mirror images of each other. Everybody say these with me. Ready? Stereoisomers. Stereoisomers. Enantiomers. Enantiomers. Okay. Diisomers. I know the diisomers is actually harder to say than you thought, right? Yeah, that's the one that really would have got you. So enantiomers are non-superimposable mirror images of each other. The molecules will be non-superimposable if there's no orientation in which all atoms of both molecules can be lined up perfectly, i.e. superimposed. So these right here are enantiomers of each other. And what you see that they're mirror images of each other, aren't they? See that? But if you were to try to go ahead and align them so they overlap, you can't do it, can you? Okay? Kind of like what? What did I use for this demonstration? My hands. And so we're going to refer to this quite often as basically handedness. Okay? Essentially like your hands. Okay? It's a very similar concept, in fact. You will notice that human beings actually have an enantiomeric structure. Okay? So, every molecule has mirror image, but not every molecule has non-superimposable mirror images. If you get something fairly simple, like for example this clip here, it's a mirror image on both sides, right? But if I were to rotate this clip, what does it look like? The exact same, doesn't it? Yeah. So it perfectly lines up with each other, right? And so this one is superimposable. It can make a mirror image. They would be superimposable. We can line them exactly up by spinning it. Okay? The superimposable mirror image compounds, again, are not going to be enantiomers. We can see an example here. Again, we can make a mirror image of this compound. If we were to just then rotate it, we can line everything up again. Okay? So, not an enantiomer. So let's go ahead and talk about the guiding principles for drawing a molecule's mirror image. So an atom and its mirror images have to be directly opposite each other and opposite sides of the mirror. If you just literally think about it as taking a mirror image and drawing that out, it really does help you, because you're quite used to mirror images, aren't you? Probably experience a mirror image every morning, right? Okay. Now, an atom and its mirror image are going to be identical distances away from the mirror. When the mirror is placed next to a molecule, your dash wedge notation in the mirror image is going to be identical to that in the original image. So let's go ahead and do this. Here we have a start. So what we're going to do is we're going to take that carbon and draw it an equal distance on this direction. Is everybody okay with that so far? Okay. Okay, so all of the bonds around the carbon now have to be reflected as a mirror image, right? And so what's going to happen is now this chlorine on the right is now going to be on the left. It's still going to have the same dash wedge notation. Okay? So it's still a line in the plane of the paper, right? It's just on the other side. Okay? Okay, and then the next one we're going to do is the next easy one. Hydrogen. Hydrogen's still a line in the plane of the paper, and now it's on top, right? Same as it was before, because there's no difference. Everybody okay with that so far? Okay, so the next one is going to be, we need to put the fluorine, don't we? Okay, so the fluorine's going to go from, it's on the left right now, it needs to now be on the right for the mirror image, doesn't it? Remember, the wedge dash notation doesn't change. Okay, so that fluorine is still coming out towards us, just now instead of being on the left of the molecule, it's on the right side. Just like your thumbs, right? Okay, and then the bromine now. So the bromine was on the left, now it's going to be on the right, and again it's going to have a dash notation, right? Okay, is everybody good with that so far? Okay. Note that we have now made mirror images of each other. If we try to rotate one into the other, what do we notice? Yeah, they don't match, do they, if we try to rotate them? What ends up happening is the fluorines are coming out towards you in both directions, right? If you rotate one over the other, the fluorines end up pointing away from you for one and towards you for the other, don't they? Okay? Yeah, I know. Yeah, pretty crazy, right? So this is typically referred to as chiral and achiral, okay? Literally, chiral, do you know what chirality stands for? What that word actually means? Hand. Is it handedness? Okay? A molecule is going to be chiral if it's an enantiomer. If you can make a mirror image that cannot be superimposed, literally exactly like your hands, right? Woo. I know. And so chirality easily done with your hands and easily thought of with your hands, okay? Molecules that are achiral do not have enantiomers. You can't make an enantiomer of them, and so they will not have handedness. Anytime you do a reflection, you're always going to be able to superimpose them back over each other, okay? And so we actually see some examples right here. The hand would be what? Has to be chiral, right? Or else the word doesn't make any damn sense. This right here, is that chiral or achiral? Yeah, achiral, right? Because it's too simple. Okay. This right here, chiral or achiral? Okay, so if you tried to rotate those and superimpose, the shell has depth to it, doesn't it? I know it's a little difficult to see on two dimensionals, but so they would not actually superimpose, would they? If you rotate it. So it'd be chiral. Yeah. Okay, so this right here is the Q&A. If anybody has any questions about the material, the questions would have popped up, okay? So if you ever have a question you don't want to interrupt my flow, and you're like, just wondering, don't really want to interrupt, or you're just shy for whatever reason, you don't want to, have people look at you, right here, okay? Okay, so determine whether trans 1,2-dichlorocyclopropane is chiral or achiral. Okay, so is this chiral or achiral? Everybody have it down? Okay, I'm going to switch to the problem now. Everybody ready? Okay. You should be getting options of whether it's chiral or achiral for the previous problem. Okay, everybody good? Okay. All right, so if nobody stops me, I'm going to go on. Okay, is it chiral or achiral? You got 15 seconds. Dun 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 dun. Okay. All right, so majority of people said chiral, some said achiral, and it was chiral. Mm-hmm.
So, when you said earlier about the shell, if it has depth, like how would this one like?
So, the easiest way to always do this is to go, how many objects are around it? Okay, ready? So if we look at this chloride right here, around this carbon here, see that? Okay. So the easiest way to tell this is, number one, you could just try to envision this, right? If we were to try to reflect everything, what we would end up doing is a mirror images. Ooh, I froze it. There we go. Mirror images, this would be the mirror images. See that okay? Okay. So then if we tried to rotate these into each other, what we would see here is that this chlorine would actually end up going into the plane, right? Rather than out of the plane. Can you guys see that? Okay. The other way to deal with these, and this requires less three-dimensional analysis in your head, is to go, how many objects are around it? Why is my hand chiral? Yeah, it's the fingers, right? Like if it was just the palms, I could rotate these around and match, right? It's the dang fingers that are causing me problems. It's that this dang thumb here, well, the fingers are all different, aren't they? And this dang thumb is on the wrong side, isn't it? Okay? And so that's what's messing up my ability to match, isn't it? See that? My middle fingers are too big, my other fingers too small. That's messing up my ability. And so it's the number of objects that are around a central point that cause that chirality. Okay? That's why the shell was also chiral, because it had those patterns, right? And so it had hundreds of objects around a central point, didn't it? Trying to match up those hundreds of objects is not possible. And so if we look at this, the quick and easy way to determine this is actually to look at the carbon right there. How many different objects would be around that carbon? There's the chlorine. There's this side of the molecule, right? Which is different than this side, isn't it? Okay, and then there's a hydrogen as well, isn't there? Okay, And so there's 4 objects around that carbon, and that's going to always end up being chiral. Because there's 4 different objects, you can't actually reflect all of them and it match up and be symmetric. Okay? If you only have 3 different objects, because you have like 2 hydrogens or something, that's going to end up being achiral, okay? Okay. And again, it'd be like taking away some of your fingers. You could start matching things up a lot easier, couldn't you? Okay? Or for example, if you start looking at this right here, around a central point, we only have 3 objects, don't we? The top and these 2 flanges, right? The flanges actually match. And that's why that plane of symmetry, that's why that is achiral. Okay? Okay. That's the faster way to do it, is how many different objects do I have around a central point? Okay? But you can also reflect it through, make a reflection in your head or on paper, and then see if you can rotate it back in. Okay? Okay. And so we see that we cannot rotate it back in. Any way we rotate it, the chlorines don't match, do they? Huh? What's up? No, were you trying to ask a question or no? Okay, okay. Okay. And there's those. Okay, so let's look at a plane of symmetry test for chirality. A molecule has plane of symmetry if you can bisect it in such a way that one half of the molecule is the mirror image of the other half. This has a plane of symmetry. My little alligator clip up here, right? Okay. Humans, externally at least, have somewhat of a plane of symmetry. Okay? That's that symmetricness. Okay. Okay, so a molecule that has a plane of symmetry has to be achiral, because you can't end up reflecting it in any way that would break that symmetry, could you? Can everybody kind of see that? That internal plane of symmetry means automatically that both sides are the same, doesn't it? And so if you rearrange those sides, one left, one right, doesn't matter. For example, when you look in the mirror, what happens to your reflection? Does it look particularly different than you look? Not really, because we're symmetric, right? Ish. Okay. So this is actually what we're seeing here. Can you guys see that this has a plane of symmetry right there with those hydrogens? And then the sulfurs on both sides? Yeah? Okay. Or the fluorine and... Yep. So these hydrogens create a plane of symmetry right here. And that means that the mirror reflection of this ends up never being able to be non-superimposable. It's always superimposable, has to be, because we have those 2 hydrogens, right? That creates our plane of symmetry right there. Everybody see the plane of symmetry okay? Mm-hmm.
So even though it's got chlorine and fluorine, 2 different atoms.
Yeah. We only have 3 different things, or we have a plane of symmetry in it, right? Yeah. The hydrogens and this carbon here make that symmetric. If there was anything else than a hydrogen right there, it wouldn't be symmetric. But that being another hydrogen has to be symmetric then. Okay? That makes sense?
I'm just confused about how the fluorine and fluorine, because the whole thing has to be symmetric, right? For there to be a plane of
No, it has to be symmetric through a plane.
Yeah.
Yeah. So if we look again, let me exit out and exit back in. Okay. Okay, so a plane of symmetry is a plane around which you're symmetric. Okay? For example, you have a plane of symmetry dissecting you this way, right? Okay. Now, you have different objects on the 2 sides of you, don't you? You have your right side and your left side. Okay? For example, your hands are not superimposable, are they? No. And so you're actually very similar structure to this. Okay? You have a front and back, don't you? See that? And so that would be like your fluorine and chlorine here. Fluorine's your front, chlorine's your back, right? Yeah. And so this is that plane of symmetry. See the blue thing?
Yeah.
That's the plane of symmetry. And so if you look at the two sides, they look exactly the same on both sides of that plane, don't they? And that's the symmetry part. There are higher orders of symmetry. We're not going to get into that stuff. And that would be symmetric across and to side by side, and you can have higher and higher symmetries. And it does some pretty crazy stuff, but we're not even going to touch on that. That's way beyond the course. Note that if you have something else here, see how we can replace one of the... What the hell? We can replace one of the hydrogens, like over here, and that breaks that plane of symmetry. So no longer a plane of symmetry. That is chiral. Okay. Okay, I guess I'm actually out of time, aren't I? Okay. You all have a great day. I will see you Friday for most of you. They smell of it. Hi.
Can you help me
Sure.
maybe try this? So, it's with my book, okay? So, I was having some trouble with it like a while ago, and it wouldn't like let me purchase. It kept giving me, I took a